Hello, everybody. In the previous class, we have derived the expressions for ionized impurity concentrations, donor and acceptors. Those expressions will be useful in obtaining the concentration of charge carriers, electrons, and holes. But in order to make that connection, we need an extra step. We need to somehow remove the Fermi energy, an unknown parameter which enters the expressions for the ionized impurity concentration. So in this lecture, we will make that step. We will derive, first we will derive the general expressions for the electron and hole concentrations in terms of the concentrations of donors and acceptors, ionized donors and acceptors. Then we will consider a special regime which covers a broad range of temperatures around the room temperature. It is the complete ionization regime, where all impurities are ionized to a very good accuracy. Maybe not all, but 99.9% of impurities are ionized. This happens when the Fermi energy is below the donor level by more than several thermal energies and above the acceptor level by at least several thermal energies. Okay, then we will derive an analytical formula that gives you the concentration of charge carriers when only one type of impurities is present. Let's say on the donor impurities are present. That formula covers a broad range of temperatures starting from absolute zero and to going up to several hundred kelvins. So practically to the end of the complete ionization regime. Then I will talk about the ionization regimes of impurities. So the range of very low temperatures is called the freeze-out regime. And at the end of the freeze-out regime, as you increase the temperature, the complete ionization regime starts. It ends at high temperatures of, let's say, 400, 500 Kelvin, somewhere in that range. And after that, the intrinsic ionization regime begins. So we will talk about that. All right, so let's begin this lecture. Our starting point will be two equations, one of which is already familiar. It is the mass action law. It tells us that no matter how you dope the semiconductor, as long as the Fermi energy is below the conduction band edge by at least a few thermal energies and above the valence band edge by at least a few thermal energies, you can use Boltzmann's approximation in evaluating the charge carrier concentrations and not P0. And within the range of validity of Boltzmann's approximation, the product of charge carrier concentrations, electrons and holes, equals the intrinsic concentration squared, and not P0 equals n intrinsic squared. The second equation, which is actually written as first on this slide, expresses charge neutrality. It's almost obvious, or maybe not almost. It is obvious. It should be obvious. So the whole semiconductor, no matter how you dope it, but it must be electrically neutral, which means that the total concentration of negative charges must be balanced by the total concentration of the positive charges. What are our negative charges? Well, they are mobile charges, electrons in the conduction band, more precisely, and stationary charges, ionized acceptors, right? When an acceptor gives out a hole to the valence band, it actually takes an electron from the valence band and turns into a negative ion. So these are our negative charges. The positive charges are, of course, the mobile ones, holes, which are free to move in the material, and ionized donors. Again, when a donor gives an electron to the conduction band, it turns into a positive ion. And the sum of negative electron and negative acceptor concentration must be equal to the sum of the positive hole and positive donor concentration. Good. So we have two equations for two unknowns. Let us pretend for now that we know what the concentration of ionized donors and acceptors are. Let us just pretend. In fact, we do not, but let's pretend that we do. Then you can solve these two equations for two unknowns, N naught and P naught are our unknowns, analytically. Let's say your semiconductor is of N-type. That is, your donor impurities dominate. The concentration of ionized donors exceeds the concentration of ionized acceptors. In that case, the recommended procedure is to first express the whole concentration in terms of the electron concentration using the mass action law, P naught equals N intrinsic squared divided by N naught, and plug in this expression for P naught into the charge neutrality condition. This gives you N naught plus N acceptor minus equals N intrinsic squared over N naught plus N donor plus. So this and this is the same thing. What do we get? We get a quadratic equation. Multiply both sides with N naught squared plus N acceptor minus N donor plus in the brackets times N naught minus N intrinsic squared equals 0. Quadratic equation. We know how to solve quadratic equations. This is the solution. Once you have the electron concentration, you can get the whole concentration using the mass action law. If your semiconductor is of p-type, you start by expressing electron concentration in terms of the whole concentration, plug in the expression for electron concentration here into the charge neutrality condition. You will get a quadratic equation for P naught, whole concentration. Solve that quadratic equation for whole concentration. This is your result. The expression is similar to the electron counterpart, except that donors and acceptors interchanged. Now, mathematically, both formulas, both approaches are equivalent. But numerically, I strongly recommend that in your numerical calculations, you use the first approach. That is, for N-type semiconductors, you use the first approach. That is, find electron concentration in terms of the impurity concentrations, using this long expression with the square root, and find the whole concentration using the mass action law. And for P-type semiconductors, use the long expression for whole concentration, use mass action law for minority electron concentration. The reason why I suggest that strongly is because of the potential numerical error may happen if you use the wrong procedure. So let's say your semiconductor is N-type. Your majority carriers are electrons, your minority carriers are holes. Let's say, for definiteness, that your intrinsic concentration is 10 to the 9th charge carriers per cubic centimeter, 10 to the 9th. And let's say your donor concentration is, I do not know, 10 to the 18th. Okay, 10 to the 9th versus 10 to the 18th. Okay, and let's say that you forgot about my advice and you decided to use the second approach. You decided to use this long expression for whole minority whole concentration. This is what you will get. Look at the expression under the square root. N intrinsic squared. N intrinsic is 10 to the 9th, N intrinsic squared is 10 to the 18th. Look at this formula, at this part. And donor is 10 to the 18th, and donor squared is 10 to the 36 divided by 4, so 0.25, 10 to the 36. 0.25, 10 to the 36 plus 10 to the 18th differ by 18th or 17th, okay, 17 orders of magnitude. When you add up two numbers that differ by 17 orders of magnitude, the smaller number will get neglected numerically. So the square root will have the value of square root of donor concentration squared divided by 4. Intrinsic concentration will vanish when because of the finite number of digits that your calculator can take into account. So you have the square root of n donor squared divided by 4, which gives you just n donor divided by 2. N donor divided by 2 minus n donor divided by 2, the difference is 0. Okay? Whereas the actual value of the intrinsic, of the hole concentration will be 1 hole per cubic centimeter, provided that all impurities are ionized. Okay. So next, I would like to make this comment. Let's say your semiconductor is of n-type. It is not true that the concentration of electrons is the sum of intrinsic concentration plus ionized donor concentration. It could be naively expected that, so my electrons in the conduction band, they come either from the valence band or from donor levels, from donors. And so you just add up the donor concentration and the intrinsic concentration, and that will be your electron concentration. No, it's not. It's not a correct conclusion, because some of the electrons which are given by the donor impurities to the lattice end up not in the conduction band but in the valence band. And it is for this reason that hole concentration is also affected by the donor impurities, mass action law. The more electrons you have, the fewer holes you have, and vice versa. And not P0 equals n intrinsic squared. And that's exactly because some of the electrons that are, again, given by the donor impurities end up in the valence band, thereby eliminating a big chunk of holes which would be present there otherwise. And same, of course, applies to acceptor impurities. So the concentration of holes is not the intrinsic concentration plus acceptor impurity concentration for the same reason. Some of the acceptor impurities may take electrons not from the valence band, but from the conduction band. All right. So this is what we have so far. Electron and hole concentrations expressed in terms of the effective densities of states, Nc and V, in the conduction band and in the valence band, multiplied by the probability for a particular state to be either occupied by an electron, that's for electrons, or to be unoccupied, to be empty, that's for holes. So this is one set of formulas that we have derived. The second set of formulas relates the ionized donor and ionized acceptor concentration in terms of the total donor and acceptor concentration, and it involves parameters like impurity degeneracy. For donors it is 2, for acceptors it is 4, oftentimes. Then in the denominator you have this exponential, so for donors, ionized donor concentration. In the exponential you have Fermi energy minus the energy of the donor state, ED, but the energy of the donor level is below the conduction band H energy, EC, by the amount of donor ionization energy, E donor ionization. So ED equals EC minus E donor ionization. This is what we have written down here. E Fermi, this is E Fermi minus ED. ED is EC minus E donor ionization. And this whole story is divided by the thermal energy KT. Now look at the electron concentration here. We see E Fermi minus EC divided by KT. And here we have E Fermi minus EC divided by KT. So this exponential to the E Fermi minus EC over KT in the formula for donor, ionized donor concentration, can be replaced with the ratio of electron concentration to the effective density of states in the conduction band, like this. We have eliminated Fermi energy in the ionized donor concentration. All that matters is donor ionization energy and electron concentration. So we have related ionized donor concentration to electron concentration. And of course, we can do the same thing, the same procedure to ionized acceptor concentration, which involves in the denominator exponential to the power E acceptor, so acceptor level minus E Fermi energy divided by kT. But acceptor energy is above the valence band edge energy by this small amount, acceptor ionization energy. So E acceptor equals E valence, EV plus E acceptor ionization, and exponential to the power E valence minus E Fermi over kT is just the ratio of hole concentration to the effective density of states in the valence band. So now we have two sets of equations that both of which relate electron and hole concentrations to the concentrations of ionized impurities. So this is one set, and donor plus is n donor divided by 1 plus donor degeneracy factor times exponential E donor ionization over kT times the ratio N naught over NC, and similar expression for acceptor, ionized acceptor concentration, Na over 1 plus Ga E to the power acceptor ionization energy over kT times P naught, hole concentration over the effective density of states in the valence band. So this is one set of equations. The other set of equations is either this, relates N naught to N donor plus and N acceptor minus, P naught is also given, or this, depending on the type of impurities that dominates in a particular material that you would like to consider. So two sets of equations. Each set consists of two equations, so 4 equations total, and 4 unknowns. N naught, P naught, N donor plus, N acceptor minus. 4 equations for 4 unknowns. Totally solvable, either numerically or even analytically. You can develop very efficient analytical approximations which solve these 4 equations for 4 unknowns. And in fact, you do not have to develop anything because everything has been developed before us. So we just need to use the results already obtained. One result is valid in the complete ionization regime. Complete ionization regime is when all of your impurities are ionized. Well, maybe not all, but like I said, maybe 99.99% of impurities are ionized. Good enough. In that case, you can replace the unknown parameters, N donor plus and N acceptor minus. Oh, sorry, there is a typo here. Should be N acceptor minus, not N acceptor plus. N acceptor minus with donor and acceptor concentrations, which are known. And for N-type semiconductor, the majority electron concentration is given by the Lon expression, and the hole concentration is given by the mass action law. Now, if the difference between donor and acceptor impurity concentrations is much bigger than the intrinsic concentration, then you, of course, then these two numbers, they typically differ by several orders of magnitude, or maybe more than several, maybe 10 orders of magnitude. Then you can neglect the intrinsic concentration squared in the denominator, and your electron concentration will simply be the difference between donor and acceptor impurity concentrations if you neglect an intrinsic squared. Okay. For p-type semiconductor, you use the Lon expression that involves the square root for majority hole concentration. And again, if your acceptor concentration minus donor concentration greatly exceeds the intrinsic concentration, you can neglect the intrinsic concentration here, and your hole concentration will be the difference between acceptor and donor concentrations. And your minority electron concentration, another typo, this should be N naught. Minority electron concentration will be given by the ratio of intrinsic concentration squared divided by P naught. No, so actually this expression does not have a typo, but P naught and N naught should be interchanged. All right. The Fermi energy can be found if you need Fermi energy. It can be found using, for example, the expression that relates electron concentration to the intrinsic charge carrier concentration. Like this, we have derived this expression, I believe, 2 lectures ago. So you can solve this for Fermi energy in terms of the intrinsic Fermi energy. If Fermi is Fermi intrinsic plus thermal energy kT, natural logarithm of the ratio N naught to N intrinsic. Or in terms of the hole concentration, Fermi energy is related to the intrinsic Fermi energy by this formula. Both formulas are identical in view of the mass action law. Okay, now let us consider a special case when you have only one type of impurities present, for example, donor impurities. Then you can derive an accurate expression for electron and hole concentrations, and that accurate expression remains accurate both at low temperatures and up to temperatures where the intrinsic concentration becomes comparable to the concentration of ionized impurities. So that's the intrinsic regime. So an intrinsic regime starts at relatively high temperatures, let's say 500, 600 kelvins. Very hot temperatures. Humans cannot survive on those temperatures. All right, so let's say we have only donors. Acceptor concentration is 0. The concentration of ionized donors is, well, we can say that at normal temperatures, around the room temperature, and especially at low temperatures, cryogenic temperatures, the concentration of ionized donors is typically much higher than the intrinsic concentration. Why is it so? Well, first, because doping a material just with, let's say your intrinsic concentration is 10 to the 10th, it is silicon, it makes very little sense to introduce donors at the concentrations of 10 to the 9th, because you're practically not affecting your charge carrier. You need to have some control over your electron and hole densities, and for that you need to dope the material at the levels which greatly exceeds much higher than the intrinsic carrier concentration, carrier density. So at room temperatures, when all impurities are ionized, all donors are ionized, your donor concentration is much bigger than the intrinsic concentration. Now let's say you are decreasing the temperature, make the temperature lower and lower and lower. Intrinsic concentration decreases as exponential to the power minus the band gap divided by 2 kT. This is a very sharply decreasing function. At very low temperatures, now, in order for an electron to move, to be transferred from the valence band to the conduction band, electron needs an energy of the order of the band gap energy, kT, right? Well, at least the band gap energy, kT, which is like, let's say, 1 electron volt, big. In order to be promoted from the donor level to the conduction band, an electron needs much smaller energy of the order of, let's say, 0.1 or 0.05 electron volts, depending on the type of impurities. So if donor concentration, ionized donor concentration, is much bigger than the intrinsic concentration at room temperature, then it will be much bigger than the intrinsic concentration at any temperature below room temperature. Okay, for this reason, because the energy to go from the valence band to the conduction band is much bigger than the energy to go from the donor level to the conduction band. Band gap is much bigger than the donor ionization energy. Now, in that case, we can approximate the concentration of electrons with the concentration of ionized donors, just because using this formula derived above, and keeping in mind that n acceptor is 0, n intrinsic is much smaller than n donors, you can neglect n intrinsic and approximate the electron concentration with the concentration of ionized donors, which is written down like this. And here I wrote down explicitly the donor degeneracy factor set to 2 for spin up and spin down. So I have these two expressions for the electron concentration in terms of the ionized donor concentration, and the general expression in terms of the effective density of states. Now let us denote this exponential E Fermi minus EC over KT. Let us call it X. So the electron concentration can be written down on the one hand as the product of NC times X, effective density of states in the conduction band, times X, which is this exponential. And on the other hand, it can be written down as N donor divided by 1 plus 2x, 2 times exponential E Fermi minus EC over KT, it is x, times E donor ionization over KT. Multiply both sides of this identity with the denominator of the left-hand side, you get a quadratic equation that you can solve. And we know how to solve quadratic equations, and here is the result. So once you have this x, which is E Fermi minus exponential to the power E Fermi minus EC over KT, once you have this x, and you see it involves the parameters that we know, donor ionization energy and KT. So once we have x, we can have the concentration of electrons. We can have the concentration of ionized donors. Like here is the concentration of ionized donors, which is the same within this approximation. This formula, this analytical formula, is valid in a broad temperature range that covers about absolute 0 up to the regime, up to the temperature at which the intrinsic concentration, so intrinsic concentration increases with temperature. So eventually, whereas the donor concentration does not increase in temperature, it is fixed. So eventually, as you increase the temperature, intrinsic concentration will become comparable to the donor concentration. And this is the intrinsic regime. All right, and so here are the three regimes, three ionization regimes of impurities. I assume that in this plot, I assume that only donor impurities are present, and I took the donor concentration to be 10 to the 15th. These are the typical values for the effective densities of states in the conduction and the valence band. I took them for simplicity's sake to be 10 to the 19th. The band gap is taken to be 1 electron volt, and the donor ionization energy is taken to be 0.05, so 50 milli-electron volts. The curves obtained here show the Fermi energy as a function of temperature and electron concentration, solid line in the second and the lower panel, and hole concentration, the dashed line in the lower panel. as a function of temperature. So the temperature goes from 0 to 1,000 kelvins. I'm not sure. Typically, materials melt at 1,000 kelvins, but let's say this particular hypothetical semiconductor does not melt at 1,000 kelvins. All right. The curves are obtained numerically by solving the two equations for two unknowns. So we have equation 1 is the concentration of ionized donors. Equation 2, in terms of the electron concentration. Equation 2 is the electron concentration in terms of the ionized donor concentration. So equation 1 was this. Equation 2 is, is this, with n acceptor set to 0. Okay. So I solved these two equations for two unknowns numerically, and this is what I got. Here are the curves. So at low temperatures, between absolute zero temperature and about 500 kelvins, or maybe 100 kelvins, so in this very low temperature range, electron concentration very quickly goes to 0 on cooling. This is the so-called freeze-out regime. In the freeze-out regime, electrons go from the conduction band to the donor ions, turning the donor ions into donor neutral atoms with the hydrogen-like electron energy. So in the freeze-out regime, the Fermi energy approaches the value which is halfway between the donor energy and the energy at the conduction band edge. So it is 0.025 electron volts below the conduction band edge energy. So if I decrease the temperature further, this would go to the value 0.975 electron volts. So the energy is measured from the bottom of the valence, from the top of the valence band. Okay, and electron concentration decreases very quickly as you cool down the system further, below 100 kelvins. Above 100 kelvins, we enter the complete ionization regime, where electron concentration equals, to a very high accuracy, the donor concentration 10 to the 15th inverse cubic centimeters. And hole concentration is given by mass action law, N intrinsic squared divided by electron concentration. That's your hole concentration. Hole concentration increases as the temperature is increased, because N intrinsic increases as the temperature is increased. Now, of course, the Fermi level, as the temperature is increased, the Fermi level shifts down closer and closer to the band gap, to the middle of the band gap. Eventually, you reach the temperature where the complete ionization approximation is not valid anymore. This happens when the intrinsic concentration becomes comparable to the concentration of your donors. Right? The intrinsic concentration increases as you heat up the system. So for this choice of parameters, this happens at the temperature of about 500 kelvins. Okay, no, it's 450 kelvins. 450 kelvins. So you enter the intrinsic regime. In the intrinsic regime, eventually, as you keep increasing the temperature, the intrinsic concentration starts to greatly exceed the concentration of donors, all of which are ionized, also in the intrinsic regime, of course, but donor concentration is a fixed number. It doesn't increase with temperature. Intrinsic concentration does. So in the intrinsic regime, the semiconductor behaves as an intrinsic semiconductor. No matter how you doped it, your concentration of electrons will be approximately the same as the concentration of holes, will be approximately the same as the intrinsic concentration and intrinsic, and it increases with temperature. And in this intrinsic regime, the Fermi energy is exactly in the middle of the band gap. Why? Because I chose the parameters. So see, the equality of the effective densities of states at 300 kelvins, 10 to the 19th inverse cubic centimeter, implies that the electron and hole effective masses are the same. So Fermi energy, the general expression for Fermi energy is the energy in the middle of the band gap in the intrinsic semiconductor. It's the energy in the middle of the band gap plus 3/4 thermal energy times natural logarithm, the ratio of the effective masses of the charge carriers. Oh, I forgot which mass is in the numerator, which one is in the denominator. But so this second term does not play a role for these parameters. So that's that. Thank you all very much for your kind attention, and I'll see you in the next lecture. I think we are done with semiconductors in equilibrium. Goodbye.